All right, section 3.6 is called optimization. Optimization is, generally speaking, us trying to optimize or find a best solution for something. So, for example, you might hear language that says something like, we want to find the lowest cost for making our t-shirts. We want to find the largest profit for selling the t-shirts. So you're trying to find either the biggest or the smallest something that you're trying to do it with. Maybe you're trying to enclose an area of a fence. I think that's my first example. You want to find maybe the biggest amount of area that your dog can run around in. Or maybe you're wanting to minimize the least amount of fence you can use to do it with. Okay, so it's always about finding the biggest or the smallest something. Well, biggest and smallest something sounds an awful lot like maxes and mins. And maxes and mins with calculus are found how? Derivatives. And we set them equal to 0, right? That's how we're going to do this. So I'm going to give you kind of a list of how we go about solving these problems. Often, there's a visual that we can draw. Maybe it's a list of values. Maybe it's an actual picture that we can draw, okay? Maybe it's a table that we can create, but something that gives us a visual for what's going on. It doesn't always happen. There's not always a visual, but there often is. The second thing is to identify what you know and what you need to find. The third thing is to write any applicable equations. Identify what it is you're trying to make the biggest or the smallest. What are you trying to optimize? And then we need an equation that's only got one variable in it on the right-hand side. You'll see that happen in, I think, the very first example where it's like, oh, we got to do something different. I can't have two variables over there and continue in this problem. Let me just pause for a moment and tell you, you can actually do this with two variables. It's called multivariable calculus, and that's a Calc 3 topic. A few of you are going to head up that direction at some point, so you will get to do that, but not today. And then after you figure out what it is you want to optimize, which variable that is, you're going to determine the maximum and the minimum allowable. This has context, right? If I'm actually talking about the fence and I've got my yard, I can't use part of my neighbor's yard. I have a limit on how big my area is that I can use. Okay, so there are some natural constraints in the way the problems are set up. There is some natural constraints we have to consider. And then the last thing, of course, is to use the calculus that you've been using in the last 2 or 3 sections to actually find that maximum or minimum value. Okay? So the calculus part of it in these problems is usually not the biggest part of the problem. It's the setup that's the biggest part of the problem. Okay? So notice I didn't say necessarily hardest. It's just the most time-consuming is what I'm referencing. All right, so here's our first example. We've got a 3-sided fence, and we're going to build it next to a straight section of river. The river is going to form the 4th side of a rectangular region. So we're creating a rectangle, right? But our rectangle only has 3 sides that are man-made. The 4th side is the river. It says the enclosed area is supposed to equal 1,800 feet squared. So we know the area that we're going to enclose. We're wanting to find the minimum perimeter and the dimensions of the corresponding enclosure. Okay, so what is the first step I'm supposed to do with these problems? Draw. And we can draw a picture for this one, right? Yeah. So that's where we're going to start. We're going to draw ourselves a little river over here. That's my version of a river. It's blue, so I think I get credit for that, right? Yeah, definitely. And then I need to draw what next to my blue river? What shape are we doing in the air? A rectangle, you bet. I'm going to draw a rectangle, and we recognize that the blue, although it's not completely straight, is supposed to be marking out for us as though it were a straight line for a rectangle. And that's the image that we have. We have a rectangle here. Tell me some things you know about this rectangle in terms of its dimensions. What do you know? 2 sides are the same, right? The way I've drawn it, it's the top and the bottom. So whatever they are, we can give them the same name. So what name would you like to give them? X. So Jen's put an X and an X right here. Everybody good so far with that? Okay. The 3rd side, could it also be X? Could it be? It could, but does it have to be? No, it wouldn't have to be an X, right? So we need some other letter to represent what's going on the other side. So since Jen gave an X, I'm going to give a Y. There are 2 quantities that this problem talks about. What are the two equation kind of quantities that it talks about? Area and perimeter. All right. What did step 2 say that I'm supposed to do? Write down what we know. So what is it that we know that I haven't already written down? There's one more piece of information. The area. We know that the area is 1,800. I don't know why I put another 8 there. 1,800 square feet. That's a known quantity. And those to be found. So what am I supposed to be finding? Perimeter. So I want to find perimeter. What do you know or remember about perimeter? Okay, so in general, it's equal to 2 times x plus y. In this problem, it's not quite that, though. At least not the way I think I heard you say it. So, and maybe this is what you meant, Akil. You can tell me. Like that? Is that what you meant? Or did you mean the quantity? Usually it's the quantity. What is different about this problem that means I don't have a 2 on the y? The river is one of the sides. So in terms of the fencing that I'm actually putting up, I only have 3 sides of fencing, here, here, and here, right? So I really have x plus y, and that's 2x plus y. Now, what is it that wait, I'm getting ahead of myself. What was step 3? We got equations. What else does step 3 have something supposed to do? Okay, so what are we supposed to optimize? What are we trying to optimize in our problem? What a great question, right? What does optimize mean? Finding what? Minimums and maximums. So what does this problem say that I'm wanting to either maximize or minimize? Find the minimum perimeter. Jacob found it in there. Okay, so it says find the minimum perimeter. So what is it that I'm trying to optimize here? It's perimeter. So this equation right here is the one that I'm going to be using to find derivatives eventually. But there's a problem right now. What's the problem? There are 2 variables on the right-hand side. You guys with me? I can't have 2 variables on the right-hand side and proceed with this problem. So somehow I have to use other information that's on the screen to make one of those variables written in a different way. Okay, there's one other thing that I do not have written on the screen. Anybody recognize what it might be or what might be useful to have written on the screen? Mm-hmm.
Why do we not include 2 y's? Because I understand that the river is one of our sides.
Mm-hmm.
So
We're wanting to minimize our building materials, and we're not building over there. Exactly. Yeah, it's not really minimize. I mean, it is minimizing the perimeter, but for the purpose of minimizing the fencing. Yeah. Yes. Any ideas, Jen?
Something to do with like the dimensions of the corresponding?
It is something to do with those dimensions. What about the area, Josh? An equation for area might be helpful. You're exactly right. Do you know an equation for area? Yeah, the variables I've used, it would be x times y, right? So over here, this area formula, why would it be helpful potentially to have a formula for area? All right. I actually have a formula that says x times y now is equal to 1,800. Why is that helpful? Okay, this is what Akil's telling me to do. He's telling me that once I have an equation with x and y in it, I could actually use that to get rid of that variable over in perimeter that's being unhelpful at the moment. Does that make sense? This is how these problems generally play out, is that there's some way that I can eliminate one of the variables based on the other piece of information. In this case, the area is the other piece of information that I'm actually given. So over here, my problem, my perimeter is 2x plus 1800 over x. What if I had decided to solve my equation for x equals? Would that be okay? Sure, no problem. I just end up with an equation in terms of perimeter that's only in terms of y. Okay, so the work will look a little bit different, but you'll end up with the same solution. All right, let's see. We determined, we've done step 3, we've rewritten the equation in terms of one variable. What does number 4 say is going to happen in this problem? There are some natural constraints on this x and this y. So taking a look at x and y, what can you tell me about x and y in terms of the problem itself? What's a minimum value for both of them? What do they both have to be larger than? 0. Why? Right. Yeah. It can't be negative. And if they were equal to 0, I wouldn't have a rectangle, right? So I would have no area. And I do have area. It's 1800. All right, what about a maximum? And this isn't an exact, like, it has to be this, but just give me a sort of a ballpark. I mean, what are you thinking maybe that we're going to be getting for a maximum for x or for y? Yeah, I mean, probably not any bigger than 1800. If one of them's 1800, then the other ones are going to be very, very small. We're going to end up with this tiny little strip along the river, and that's not much area, right? I mean, like, I can stand and I can walk, and that's about it. I can't do anything with it. So it seems reasonable that we're probably looking at something where the x value and the y value are also both smaller than 1800, at least. Okay, there's nothing exact about that. It's not exactly correct, but that's a ballpark idea for us. They're going to be a number that's going to be between 0 and 1800. Well, technically, the x value or the y value could be as big as we want, but it automatically means that the other value ends up being fractional. So it doesn't really matter for what we're doing that we divide by the 2. But you're right that if we actually had that as a for sure hard value, that we would need to divide by the 2 to get the 900. Yeah. Okay, we've got an equation. What are we supposed to do with this equation now that we have it and we've kind of decided that my answers are going to be somewhere between 0 and 900 or 0 and 1800? You got it. All right, we need a derivative. Now, this particular equation might be more helpful to have it written as 1800 x to the negative 1. I mean, if you really want to use a quotient rule, you can. I don't have any desire to use a quotient rule when I have a function that's quite that simple. So I'm going to go with this. Yes, we're on step 5, exactly. We determined the maximum minimum, that's the x greater than 0, less than 1800 bit. And then step 5 is using calculus. All right, so what's the derivative of 2x? 2, we like that one. What's the derivative of 1800x to the negative 1? Wonderful. What am I supposed to do with this now? All right, I'm supposed to set it equal to 0. Now, if you want, you can change that back into 1800 over x squared. That's fine. If you don't, you could deal with it directly. I kind of am a fan of not dealing with negative exponents, so I kind of like the idea of turning it back into the 1800 over x squared part. That makes it a little bit easier in my mind to deal with. Now, you might look at that and think, it doesn't equal 0. Well, it's because we don't have the common denominator part yet, so you don't really see it happening quite as clearly yet. It will equal to 0. How will I find that? There's several ways I could do it. What would you like to do?
Multiply x squared to 2.
Okay. All right, so Snyder would like to multiply x squared by everything, basically, right? Like that?
Well, yeah.
That would get rid of a denominator, wouldn't it?
Yeah, but I was thinking like making 2 over 1, so it's...
Okay, so then we could do it that way, and it would look something like this. You wouldn't be multiplying by x squared, you'd be multiplying by x squared over x squared.
Yeah.
We could do that. Okay, we'll go with that, since that's the first one I heard. So this would give me 2x squared on top, minus 1800, over x squared on bottom. At this point, where will this equation, or this expression, equal to 0? Yeah, the numerator, right? This is the same kind of thing that happened when we were sketching graphs. It's going to happen when the numerator is equal to 0. So it's going to happen exactly when I have the 2x squared minus 1800 equal to 0. And some of you might notice that's exactly what would have happened if I'd actually multiplied everything through by x squared instead. So you end up at the same spot either way. How am I going to solve this? All right, so Jen said we're going to add the 1800 to the right. And we're going to divide by 2. So what does x squared equal? Well, x squared first is 900. And then what does x equal? You guys are ahead of me, sorry. Technically, it's plus or minus 30. Now, will both of those solutions actually work? No. Which one does not work automatically? Negative 30. We already made that determination before, right? My x values need to be only positives. So the only one, so if I think, let me actually write it this way. 30 and negative 30. And the negative 30 doesn't work because it's not in my domain, is what the real issue is. The context doesn't allow that. So the only value I get is x equal to 30. If I know that x equals 30, can I get a value for y? How would I do that? Plug it in where? There is a nicest place to plug it in. Yeah, this one right here, right? Or, yeah, I think this is the one that you pointed to, Alexa, right? Yeah, same one. One of those places where I've got the direct relationship between x and y established. So my y value is found by taking 1800 and dividing it by 30. What does that give me? 60. So we are speculating that the maximum and minimum location happens when x is 30, y is 60. We haven't actually shown that that's really a maximum. And I'm sorry, it's really a minimum. We're supposed to be minimizing the perimeter, right? How can I show that this really does minimize my perimeter? There's 2 ways to do it. Sign chart's one of them. What's the other way? We can do the second derivative test. And actually, the second derivative test on this would be pretty clean because this right here was my function, right? I'm sorry, not that one. This right here was my function. 2 minus 1800x to the negative 2. So you could very quickly find the second derivative and plug it in. That wouldn't be too bad. If you don't want to deal with that, the sign chart's the one that we do the most frequently. And we plug in we put into my sign chart that x equals 30. This is a sign chart based on the first value that we had used in our equation was the value for x's. And we need to test a value on either side if we choose to go this route. So what's a value smaller than 30 you might want to test? 1. It definitely does need to be bigger than 0, right? We established that. And then a value bigger than 30? 35. And what are you plugging these numbers into? The first derivative. You're finding f prime of 1 and f prime of 35. And they aren't really f. We call them p in our function. P prime of 1 and p prime of 35. So our function over here, this one right here that's in orange or a version below it, any of those are the same function. If we plug in x equal 1, do we get a positive or a negative? We get a negative. And if I plug in x equal to 35, what do I get? It is a positive. So negative means it's decreasing, and a positive means it's increasing. So this location is a minimum, right? You have to verify that you actually found a max or a min when you're doing this. Otherwise, all you found was a critical point. So it needs to be verified. We still haven't answered the question, so let's answer the question, then we'll finish up today. It says find the minimum perimeter, and it says find the dimensions of the corresponding enclosure. We found one of those. Which have we found? We have found the dimensions. My dimensions are what? They are the x value and the y value, and the way that we typically write dimensions is we write them kind of like you see on note cards or frames. We write them like this. We're going to say it's 30, and it is feet. We're going to use the word by, or you can use the x, right? 30 feet by 60 feet. That's how you see dimensions written, something by something else, the length by the width. How do I find my perimeter? Okay, it is add them together, but not specifically just the 30 and the 60, because somebody said I should get 120, which is right. What did you do to get 120, Josh?
30 2 times 30 plus 60.
Yeah, remember my perimeter was 2x plus y? That is the perimeter of the sides that I was manipulating, right? Not the side along the river, but the other two sides, the other three sides, excuse me. So this actually gives me 120 feet. Also notice something happened here that we haven't had happen very frequently. Because of the context, everything has units when we're done, right? So you need to be really careful that you've got the right units on them. Feet, meters, those are different, right? Feet squared and feet, those are different. So be really careful that your units match the actual context of what's going on and what you're saying the answer is.